Good afternoon. Today we're going to discuss the Requs AI Predict dashboard tab, and in particular the very first sub-tab there, which shows the prediction results. As you can see on the screen, there's 4 frames: the size results, the defect prediction results, the failure rate results, and reliability availability. We're going to take each one of those panels and I'm going to show you the calculations that were used to come up with all the numbers you see there. If you press the help button in your software, the help file will be displayed, and you can see here, if you tab down a little bit, it'll show you the prediction formulas. We have size, defect density, defect counts, profile, which we'll talk about shortly what that means, the failure rate, and TTF, availability, reliability. So they're actually listed in order that we're going to display them here. So if you click each of these links, for example, the size link, it will talk about how the size is computed and the inputs. So in this particular case, if we go here, the help file tells us go to the survey tab, select required inputs. Okay. So we've got the required inputs here. If we tab over to the right, you can see here the size panel on the right. We have 2 options: case lock, which is 1,000 source lines of code, and PY, which is people years. PY is people years is the simple approach. It's very easy to find out how many software people wrote the code. The number of people who write the code is directly related to how big it's going to be. So those 2 things are related to each other. They're just 2 different alternatives. In order to predict the case lock, most people have some kind of automated tool that they have purchased to be able to do that prediction. In any case, in our example, we'll go through the case lock example. It is much more complex than the people years. The first thing we're going to do is select the language type. A is for assembly, OO is object-oriented, SGL is second generation language, and H is for a hybrid, which means a mixture of second generation and object-oriented. Okay, in this particular example, they are estimating 646 1,000 source lines of code that will be written that are brand new. You can see here it's clearly a new program. There's no modified lines of code, no reused lines of code, no auto-generated lines of code. So the next 5 inputs there are largely not used. Now we get down to the last input there, which is the relative error. Size estimate is a prediction. That means there can be error in that prediction. What we have input here is a default value, which is 50%. Which means the actual size could be 50% off of what estimated. Now if we go to our help file, it explains this a little bit. Here we go. We have a definition, description of the languages there. And then we have a description of all the size inputs, which you can read. And then we get down to the confidence. The farther away the software is from being finished, meaning the earlier in development it is, the more relative error there's going to be. It's real simple. So what we have is early in development, which is when we're actually going to use this tool. This tool is used early in development. We have a confidence of 50% or more. At the opposite end of the extreme, once you get it to operation and the code's finished, the relative error is actually 0 because we know how much code there is. We know how big it is. We can measure it directly. We don't have to predict it. Okay, now the reason why you are using this tool is to predict the software reliability. So entering 0 there is probably not the right answer. It's better to enter in the conservative 50% and to keep monitoring the size during development. Okay, now let's go look at our calculations here. We have our inputs, 646,000 source lines of object-oriented code. So here's our outputs. It shows a lower, nominal, and upper bound. Now the lower and upper bounds are directly computed from the relative error, and I'll talk about that shortly. Okay, so the new e-case lock, the normalized e-case lock, normalized means normalized to one language. The first thing that is computed there is the code expansion ratio. You can see for object-oriented code, the code expansion is 6. This means that for every line of object-oriented code, there's probably 6 lines of assembler. It's a way to normalize it based on density. So we will take 6 times the new 1,000 source lines of code. There's no adjustment there. All of it is new. Modified code 0, reuse code 0, and autogen code 0. So really what that comes out to be is 6 times 646. When you multiply that out, you will get 3,876 as your nominal case. So you can see how that was computed. It's real simple, 6 times 646. All right, now the lower bounds and upper bounds. The lower bound here, since our confidence value is 50%, we take 3,876 minus half of it. So if you take 3,876 minus 1938, which is half of it, you get 1938. So this is essentially half of that, because our relative error was 50%. Now the upper bound, we take half of this nominal value, which happens to be 1938. We add it to 376 and we get 5814. Okay, so that's how we got our bounds. Now, if at any time the bounds should change, we become more confident, then they will be changed over here. Let's just type something in and see what happens. Let's type in 2, for example. Let's make it simple and make it 0.1. Refresh that. And you can see now those bounds are very close together because the relative error is only 10%. So let's go back and change it back to our original number there. Okay. And we'll move on to the next example. So now let's look at the defect predictions. The first thing that's predicted is defect density. It's predicted at 2 milestones, operation and testing. And so the operational defect density, you can see there's clearly smaller than the, let's get to our help page here, is clearly smaller than the defect density in testing. That's honestly what we'd like to see. You know, during testing is the time to be finding defects, not in operation. These two numbers here are generated from the machine learning model. So the way the machine learning model generates that prediction is from all of the inputs that you had under customer, inherent risks, software personnel, planning, execution, software requirements, design, code, unit testing, which is testing by someone else, someone other than the person who wrote the code, corrective action, configuration management, defect tracking, reliability practices, software quality assurance, and software processes. So when you answer these questions, you can see there's going to be times when you don't know the answers. The machine learning model will ignore any questions you didn't know the answer to, and it will predict a defect density based on the other programs that we have in the database. So you can see all the inputs there. Okay, so in this particular case, we have a defect density of 0.114 for operation. That means defects per normalized 1,000 lines of code. Okay, so the next thing we're going to want to do is predict the total defects, which is simply the size estimate here, which is a normalized effective case lock, times the defect density. So this table right here is simply this table multiplied by this table. So if we look at, let's take the nominal bound first. Okay, so 3876 times 0.114 is equal to 442.7269. We'll just round down here. Round approximately equal to 443. If you type that into your calculator, you will see it comes out to 442 and some odd number. Okay, if we do that for the lower bound, 1938 times 0.114 will give us 221.363459. Upper bound, 5814 times 0.114 will also give us the upper bound there. Now for testing, we do the same thing. The lower bound times 1.256. We get 2434, almost 2435. The nominal size, 3876 times 1.256 gives us 48, around 4870. And then the upper bound of 5814 times 1.256 will give us the upper bound on testing defects. Okay, so those are pretty simple calculations.